All right. Good morning, everyone, and good evening for those on the other side. Thank you all for being here. It's a great pleasure to host our second talk of this exciting seminar series. My name is Joseph Bokarji, and I'm a postdoc at the University of Washington, working with Professors Steve Brunton and Nathan Kutz. I am one of the co-organizers of this series, along with three other postdocs, Jason Bramberger, Jordan Snyder, and Henning Lang. If you haven't signed up for this seminar series yet and would like to get updates on our future speakers, please check out our webpage, which I put in the chat box. Today we have Professor Michael Mahoney from the Department of Statistics and the International Computer Science Institute at UC Berkeley. Professor Mahoney works on algorithmic and statistical aspects of modern large-scale data analysis. His recent research has focused mostly on large-scale machine learning, including randomized matrix algorithms and randomized numerical linear algebra, geometric network analysis tools for structure extraction in large information graphs, scalable implicit regularization methods with applications in genetics, astronomy, medical imaging, social network analysis, and internet data analysis. He received his PhD from Yale University with a dissertation in computational statistical mechanics, and has worked and taught at Yahoo Research at Yale University and Stanford University in the mathematics departments. Among other things, he is on the National Advisory Committee of the Statistical and Applied Mathematical Sciences Institute. He was on the National Research Council's Committee on the Analysis of Massive Data. He co-organized the Simons Institute's Fall 2013 and 2018 programs on the foundations of data science, and he runs the biennial MMDS workshops on algorithms for modern massive data sets. He is currently the director of the NSF Tripods-funded Foundations of Data Analysis Institute at UC Berkeley. He holds several patents for work done at Yahoo Research and as lead data scientist for View Labs, a startup reimagining consumer video for billions of users. Today, he will present his work on dynamical systems in machine learning, combining in a principled way data-driven and domain-driven models. Michael, thank you for being here. With this, I leave the floor for you.
All right, thanks a lot. And just to check to make sure that people can hear me and see the screen and see the little hand wiggling on the screen. So let me know if not.
All right, yeah, it looks good to me.
So I don't know how it's done if people so I can't see the chat box so easily. So if there's questions, either I guess either interrupt or if you put them in the chat box, maybe.
Yeah, so maybe at the end,
to interrupt will interrupt. Is that okay?
Yeah, maybe at the end I can read the questions for you, or if you can see them, you can answer them.
All right, that sounds great. All right, so thanks. It's great to be here, and I think it's a great seminar series. So I'm glad someone's organizing. We've been thinking about some of these things for a couple of years, and so it's nice to see it sort of gaining traction. And I think it's a great and sort of very timely series. I want to talk about some work we've done on, let's say, looking at the interface between dynamical systems and machine learning. And I think people come at this, oftentimes from one side, from a machine learning side, and say, geez, these algorithms are running. One example of a dynamical system is an algorithm to solve an optimization. And if you're doing theory, you usually assume it's convex optimization problem. And then you apply it to whatever, the thing people apply it to today is to neural networks, and it's not convex in the same way. So you just call it a dynamical system and see how it works. On the other side, you have people who are, really physicists or engineers and want to solve real problems in physics or engineering. And a lot of the equations governing physical and engineering systems are differential equations. And so then it's very natural to say, I want to understand the dynamics, the temporal dynamics, oftentimes, because you want to extrapolate in time. And so we wanted to sort of try and bridge the gap between the two and try and figure out how to combine sort of in a little bit more principled way the two approaches. And so I'll talk about two things. One is a certain idea on how to build better models. And we actually know how to build improvements on the one I'll talk about. But the one I'll talk about has sort of an interesting feature that struck me at the time, that I still think sort of a relevant and sort of a good lesson. You know, we've sort of adopted a usual MO and found a regularization term and tacked it on, which is the usual MO, but it's a sort of term that just would have never occurred to you if you were an ML person. You really needed to have your dynamical systems hat on, and we apply that to a range of physical systems. And then I'd like to talk about something else that I think gets into the details in a more subtle and more significant way in terms of really trying to come up with continuous neural network models, continuous models. So this is work with a bunch of people listed at the bottom. The point on a lot of this stuff was Ben Erickson. Probably some of you know him because he spent a little bit of time at Washington, and he's been a lead on a lot of these things. So I wanted to mention him and several others on various aspects of things that I'll point to as we go through. So let's see, and I can go down. Okay, so introduction, overview, and then I'll talk about two things. One is, as I said, an autoencoder, which is a type of model. It's just a machine learning model. It's physics informed in a certain way, and I'll talk about different ways to be informed, physically informed. And we want to, predict fluid flow. And this is a canonical example some of you have looked at, and other people that do physics informed machine learning oftentimes think about. And then I'll talk about these continuous in-depth neural networks. And just because you tack a T somewhere, or a T as a subscript, and you syntactically look like there might be something temporal going on, doesn't mean that you're meaningfully continuous in depth, right? In scientific computing, there's sort of well-established methods to determine if a discretization is a good approximation or a mediumly good or only a very, very weakly good approximation, namely not so good, to a continuous function. In machine learning, we're sort of coming at it the other way, and we want to understand whether we've learned something continuous in depth. So just because you've tacked a T on and called something a dynamical system or differential equation doesn't make it continuous in depth, except just syntactically, which is not why people want to use it. So keep that in the back of your mind. And we want to develop a method to evaluate that and to come up with something better if the answer is that existing things are not continuous in depth. And that, I think, is sort of more interesting because that really gets under the hood in terms of the methodological core of what a lot of the techniques on the machine learning side are doing. But it should also lead to improvements on the applied side, not just for when you're learning continuous dynamical systems, but also for when you're not. It's sort of a natural structure to provide regularity or capacity control in the machine learning language. So just a few words sort of overview before I get to those two specific examples. This is just sort of to set the stage. I mentioned some of these things, so I could have given the preamble with these slides, but just to have a few slides that are sort of nice to look at. I mean, there's a range of, look at the, the bottom in particular. I mean, there's a range of things where people are trying to use ideas from dynamical systems and say control theory. So view residual networks as differential equations, or maybe network architectures as numerical methods or training. What is the training process? Is it really better to view it as an optimization or a dynamical system, or maybe a dynamical system you're trying to control? And so in a lot of machine learning, you're given data. There may or may not be something continuous there, and you want to learn a function. In a lot of dynamical systems, you're given a differential equation, and then you may discretize it, and you may have constraints and so on. And some of the statistical techniques, in principle could map to one side or the other, but just de facto, because in industry, certain applications are the forcing functions, you end up on one side or the other of this fence. And I think some people think certain things are obvious, and other people think that's really a much less important thing, depending on which side of the fence you come down here. So we've done a range of things. This is just a list, and I think by now this slide's a little bit 6 months old, so there's a few other things since then. And we've looked at stochastic normalizing flows. We've looked at stochastic optimization. The usual form of stochastic optimization is you anneal the learning rate or something like that to be very small to basically recover deterministic optimization. What if you keep the learning rate constant? And it turns out then, depending on the details of the problem, you get heavy-tailed structure very naturally. We have, coupled neural ODE sort of techniques using adjoint techniques in more sophisticated ways and a range of things over learning models. And so, we've done a range of different things. And the two that I want to highlight today point out two different aspects that I think are sort of more common and more ubiquitous. And so, just as an example, think the sort of basic building blocks of ResNets, which are a certain type of model, are certain sort of residual units where you learn, essentially you learn a delta. The state at time t plus 1 is the state at times t, epsilon times that, plus some delta. And so this is a Tth residual. It's a non-linear map. It's parameterized by some set of parameters theta. Here I said that those parameters depend on time. I could have had a time dependence there, but I have those parameters depending on time. That'll be important later. And you could consider a limit. You could say, well, sorry, a linear unit. X of t plus 1 is epsilon, x of t plus a linear transformation. Now, if you come from a background in differential equations, it's very natural to look at this and to say, geez, this is a discretization for, an ODE, a simple ODE. And the question is, is this syntactic form really the case or not? And so this has been used as inspiration to design new networks. But in machine learning, a lot of things are used for inspiration that really aren't true when the sort of rubber hits the road. So, there's a lot of brain analogies and stuff. So, for example, is this an inspiration, or is this really, in some sense, technical sense, the case? So this is just an example that I mentioned just because this is one of the ways we started to think about these problems. And so, dynamical systems theory is a very mature area, and you can ask, what can machine learning learn from that? And it's mainly concentrated itself on learning, I think, the long-term qualitative behavior of dynamical systems, typically described as differentials, maybe sometimes difference, but differential equations. And stability theory plays an essential role. So you want to understand the qualitative properties and knows that it doesn't maybe diverge, but it has some stability properties. And so you might be interested in studying trajectories of given dynamics. And so you may not be able to characterize the full dynamics, but you can check stability, and in simple cases, you can check it with eigenvalue sort of analysis. Now, does stability matter in machine learning? And this is, I think, worth asking yourself, does robustness matter? And stability and robustness are one of these words that can just mean an awful lot of things to different people. And in some ways, yes, definitely. In some ways, no, it certainly does not. I mean, the form of machine learning theory is I have a data set, I cut it in half, I have a training set and a test set, I train on the training set, I test on the test set. That's usually the metric people care about. There's nothing about physical constraints, there's nothing about extrapolating time, there's nothing about a world. You don't impute ontological status to the parameters you learn. They're not physically real or meaningful typically. And so stability in that sense matters much less, because the training and test set generalization, the training and test set are the same, up to expectation, up to the training test split, but they're the same in expectation. And that's very different than in a lot of physics and engineering systems, when what you see tomorrow is going to be different. You have some underlying law that may be the same, you want to learn, but what you're going to see tomorrow, the data you'll see will be different. And so stability, depending on how you instantiate that word, technically either matters a lot or really doesn't matter much in machine learning, I think. And the next, the final preamble comment is, there's a lot of work on physics informed and physics inspired and physics aware machine learning. And what does that mean, and how do you incorporate this sort of knowledge? So one way is to sort of cook it into the architecture, physics-informed neural networks. And this is what's been going on in ML for years. In computer vision, you use networks that have convolutional structures because, images have certain, geometry and spatial properties. In natural language processing, you don't use that. You use attention and other sort of mechanisms that are essentially physics knowledge. I mean, domain knowledge from natural language processing or computer vision. And so you design the architectures to have that. If you were to do a better model for climate simulation, people at LBL did this, you might cook in different architectural properties. A different thing is to say, well, I just want to train, which is what a lot of machine learning people do. I just want to train. I just want to learn a better regularizer. So the usual way machine learning people use optimization is you have an optimization function, and then you might say, well, I'm just going to tack on a regularizer. So I have F, my empirical error, and maybe this has a regularization term in it if you're doing, some regularized empirical risk minimization or something, which by the way, neural networks are not, but you write down an objective anyway. And so I optimize that plus lambda, lambda is a regularization term, times a regularizer. So this is least squares plus L1 or L2. So you're solving ridge or lasso. So it's a more complicated version of that. But the point is there, when you tack this regularization lambda on, you have two terms, and this is a parameter, it's like a temperature parameter, it's a Lagrange parameter. So you adopt a Lagrange formulation of this constraint, and you only satisfy it in a very soft way. If this is just sort of a bias you want to provide, like a prior for or against certain things, that might be fine. If this is energy conservation, that may not be so good if you extrapolate in time and your energy blows up. So there's a lot of physical things where you really want to incorporate a hard constraint. And so you might incorporate prior knowledge via essentially a hard constraint. And in optimization, these two are equivalent in a certain sense, in a certain rather weak sense. But you should really think of these two as very different. I mean, the way you solve these, the meaning of the parameters, you know, how robust they are to extrapolation time really are very different. And you might need second order techniques, you might need machine precision. And so these are really very different. And the 99% case in machine learning focuses on the one. And in a lot of cases, if you have weak domain knowledge, you want to provide a bias, this may be perfectly fine. But if it's a hard constraint, you really have to adopt the second form. And so that's something else to sort of keep in mind that we've thought about, and it's not going to be explicitly important for most of what we'll talk about today, but a little bit. All right, so two things. Physics-informed autoencoders and continuous time depth networks. But maybe I should pause for a second and see if there's any questions in the box, or make sure people are still on the line and everything's still going well.
All good. No one's asking any questions yet.
All right, so everyone's happy. So that's good. All right. All right. So Lyapunov stable. So we want to do fluid flow predictions. So this is sort of a canonical example. And you might be interested in fluid flow because you're doing climate science, you're developing better airplanes. You might be doing it because you want to get better properties of an automobile. But there's a lot of other places where it may appear sort of in a little bit more subtle ways. Or for example, if you're a self-driving car company and you want to tell if something's a stop sign, the best way to do that probably isn't look at every image, try and learn a stop sign. Is there a stop sign in the image? You might look at flow fields. You might want to understand how flow vectors behave, look at the deltas between different segments. So some of this is very obvious as physical applications. Some of this may use physical ideas in the context of the model, you know, for making classifications or things that aren't explicitly physical, but you still use the flow field lines, for example. So the setup here in the toy case we'll be talking about is, you know, assume that you have a dynamical system of interest. X of t plus 1 is a, x t plus eta. In this data-driven setting, you might only be given access to the high-dimensional observations. So you don't know what the underlying dynamics is necessarily, and you're not given access to it. So you have a sequence of observations for training data, and the objective of this work is to learn a model which maps the snapshot y of t to y of t plus 1. So if the model maps to t plus 1, then you're validating it on one step. So you could ask, how does this work if I iterate many, many times? And if there's sort of a basal level of error, it may not be bad if you're learning one step, but if you learn many steps, it's going to be important. And another thing that I see as a gotcha in a lot of cases when people do things like this is, let's say you have a data set, you know, here it is, it's 20 time slices. How are you going to cut it up? Do you cut it up, pull out randomly a training and test set so that the training data corresponds to all the time? You learn a model that's good here, so you train on the red and you predict on the gray. That does actually relatively well on the gray. What if you train on the red or the gray here and you try and predict on the red? Namely, there's a temporal axis here. You will do well here, but you may predict poorly in time. And so this is a pretty common feature of a lot of these sort of problems. So given pairs, we may train a model by minimizing a mean squared error. It could be other sort of errors. During inference time, we can obtain predictions by composing the model many times. So typically you're not interested in one step. You don't want to know what the weather is going to be like in 1 hour. You want to know what the weather is going to be like in 2 hours or 1 day or 2 days or 1 week or 2 weeks. So, you know, you iterate the time. In a lot of these scientific cases, you know that at some point it gets chaotic or something. So, you know, the detailed predictions will break. So the question is, how far out can you push that? That's not the usual question people would ask in ML. So this is just an example, just a picture to sort of illustrate the type of model. You know, we're using sort of a PyTorch framework, if you know what that is, and applying automatic differentiation techniques. But it's a typical black box models people would use in ML. And you may want to look inside the black box. So let's say that we want to add some meaningful constraints. You might have your objective plus lambda g. You know, here's your regularization. And let's say that if you're familiar with Koopman ideas, this is sort of related to that. Let's say you have a model, you want to encode it some way, you run a dynamics. In Koopman case, this would be linear dynamics, but you run a dynamics maybe with skip connections or whatever other stuff you want to stick there, and you run a decoder. And just as one step, this is just an architectural form. The ontological status of these parameters doesn't mean a lot. But if you're going to iterate this process, one of the things that you might want to do is to say, I encode dynamics decode, encode dynamics decode, encode dynamics decode. So you want the decoder dotted into the encoder to be an identity. So you might say, you know, lambda times y t minus this composition acting on y as an identity. And that's because you want to be able to iterate this dynamics. You could do something else. You could do that and tack on some other stuff. We'll get to some other stuff there in a minute. All right. Now, one of the things you'd want to ensure is the case here is that you may have stability. And the reason is if you think of just running a power method, if you run a power method and you scale your eigenvalue, your vector to be unit norm at every step, you iterate the process, you get an eigenvector, and if you do it one more time, you get the eigenvalue. But if you scale it to not have unit norm, but to have norm 1.1 or 0.9, and you iterate that process, 1.1 to the 50th power blows up, and 0.9 to the 50th power goes down to 0. So, so you're not going to be stable. So you want the analog of that. And we're going to say that a dynamical system is going to be stable if all the trajectories starting arbitrarily close to the origin remain close. There's a couple of ways to quantify this that I'm not going to get into today. If the dynamics are linear, in say the Koopman case, then the stability can be checked with an eigenvalue analysis. So this is an old idea, and if you're familiar with this, then you may know there's in particular, a Lyapunov second method, which will state that a dynamical system that we're talking about, x of t plus 1 is ax of t plus eta noise, is stable if and only if the following conditions satisfied. So this is just some condition that comes from dynamical systems theory. There's nothing machine learning here. This is textbook dynamical systems. If and only if for any symmetric positive definite matrix Q, there exists a positive definite matrix P satisfying this, that A transpose, your dynamics matrix, PA minus P is equal to negative Q. And so using this idea, we might impose, remember, omega is the learned thing. A is the dynamics we want, but omega is the learned one. We might impose that the symmetric matrix P, defined by this, you choose the right eigenbasis, omega transpose P minus, omega transpose P omega minus P is the identity. And we want that to be positive definite. So, so this is a constraint, let's call it, that we could impose in a hard or soft way, given by the dynamics. And so let's choose the right eigen. We can choose the right, we consider the case where omega is diagonalizable, which is a subset of dynamical systems, and choose Q appropriately, in which case you get omega I, pi omega I minus pi equals negative 1. Now, what does this look like? Remember, we're learning these parameters omega, and if you plot a discrete time Lyapunov function as a function of P, this is what you get, this plot down here on the left. And how would you try to enforce a condition like this? So you can enforce a condition like this by saying, I want, remember I had the term a couple slides back, this one that I'm considering tacking on as a regularization function. So it's rho acting on omega. I might adopt this form. So I want this to be 0 if P is greater than 1, nothing between 0 and 1. And I want it to be positive. Sorry, I want it to be positive if P is negative, but more positive if P is slightly negative. All right, so I want this to explode, not to explode, and not to vanish. And so I want it to be more positive. So the functional form that will get you this is the one I have on the next page, but I could choose different functional forms. But the point is this prior is not an L1, it's not an L2, it's nothing you'd come up with vanilla capacity control mechanisms in machine learning. It's really something very naturally given by the dynamics of the system and the requirement that we want it to be stable. So you can work with a physics-informed autoencoder trained by minimizing this, F plus lambda, this identity constraint plus lambda prime, this dynamics constraint, where the particular functional form I have here encodes that idea. You could optimize this, you could choose different ones. This one worked well enough for what we were talking about, so we worked with this functional form. All right. So it turns out you do a little bit better, not surprisingly, if you tack on, you know, I iterate this process and tack that on as an extra constraint. So we got some results here, and I'm going to zoom through them. But the point is we adopt a certain MO here. We adopted the form where I have some physical idea and I want to tack on various, you know, that idea as a hard or soft constraint. And so I may iterate this and tack this on with one regularization term. I may want to tack on this identity constraint as a second regularization term. I may want to tack on this Lyapunov thing as a third regularization term. You know, that does pretty well, actually. I mean, in a lot of cases, it does fine. The downside is you're tacking on lots of terms, it's lots of parameters. If all of these are satisfied in a soft way, you may ask how soft is soft. You may want this to be a hard constraint. And so we actually have better ways to solve this particular flow problem that I'm talking about here. So it's not too oftentimes you give a seminar on sort of stuff that you know has been improved upon. So if you're interested in this particular one, you know, you ping me, or you know, we have some papers up on consistent Koopman autoencoder techniques to do a better job on this particular problem. But I like walking through this because I think it was the course we took, but it's also the course a lot of people take when they're doing these sort of dynamical systems and machine learning ideas, where they say, you know, just tack on these regularization terms, which is a usual machine learning mindset. It's developing models. It's easier to develop models than to validate models, as probably you know if you're an engineer. And so this adopts the model development MO, which is what is done typically in machine learning. You just tack on regularization terms, you train, you test, you get a better one, and you declare success. And so the lessons we learned here, I think one was that was the usual MO, which was good for a lot of things, but maybe not sort of as fundamental or principled, which is what I want to get to today. And two was neat because we really had to use a regularization term that was just very different than we would have seen. And so the constraints that the dynamics would impose upon you are just very different than you'd get if you pulled a machine learning textbook off the shelf that I have over there and say, you know, would I tack on an L1 or an L2? There's no reason you'd come up with this particular functional form just on the parameters. So we apply this to flow past a cylinder, daily sea surface temperature. The long story short is that if you use a physics agnostic and don't incorporate this sort of information, blue, you know, here's a time axis on the X, the relative error on the Y, you know, the blue, the error just increases. The red, the error stays down for a lot longer. So, you know, this is like predicting the weather. You know, you're going to predict 2 days ahead or 3 days ahead or 4 days ahead, but at some point it gets worse. And so similarly here, you know, at some point you'll get worse. If I went out to 1,000, this would have gone up. And the reason is that you have some eigenvalues outside the unit circle in the physics agnostic model, and you pull them into the physics aware model. The same is true, you know, with various other sets of parameters. The red stays below the blue for a longer length of time. You know, if you look at sea surface temperatures, a more realistic and more challenging problem. The eigenvalues are actually more outside. So on a slightly less toy problem, you see the same things. You can pull all the eigenvalues in. You can pull the eigenvalues in other ways. You just add a lot of ridge regularization. They call it, what do they call it? It's weight decay. And you can pull them in, but that's a very coarse way to do that. So the point is that this regularization function adds it in a much finer way. And so you know, we have a range of other pretty pictures to justify that. Let me just, in the interest of time, not go through, but really sort of, I think, you know, flesh out that this is a reasonable approach, which is, I think, a thing a lot of people adopt. So the summary of the first part, you know, physics-informed autoencoders can improve generalization performance, cut the training test set and get better generalization. We saw that. I didn't show you, but we did see that. You could develop this with improvements with consistent Koopman techniques, and that sort of adds a little bit more of a constraint in terms of the forward-backward, do a bit better. The caveat is that we're getting sort of more complicated loss functions. You know, we have an objective plus lambda times the constraint plus lambda times a different regularization plus lambda times a different regularization. And so there's a range of next steps we can take here that, just in the interest of time, let me not go through to shift gears. But I think this is a nice example sort of the usual approach and one that I think is very successful if you start to think, you know, call it engineering scientific machine learning or engineering dynamical systems plus ML. If you really want to start to engineer stuff, this is a pretty fruitful path, I think, in a lot of ways. And the consistent Koopman follow-up that I mentioned to you is an example of that. So I want to shift gears now to talk about something else that's more recent that I think was informed by that, but really tried to get, you know, under the weeds a little bit more intimately in terms of what these models were learning and come up with sort of a more principled way to combine the dynamical systems and machine learning sort of techniques. So let me pause just for a second since I'm shifting gears and see if, make sure people are there and see if there's any questions or anything before I go on.
I think it's all good. No questions yet.
All right. All right. Everyone's happy?
Yeah,
All right. So continuous in-depth neural networks. So there's a connection that's gotten some attention recently between ResNets, which are certain class of models, and dynamical systems. And ResNets are one of the vanilla architectures, just a textbook you pull off the shelf architectures that basically say you have some X of t. Lots of times in machine learning, you draw pictures like this rather than writing it as a functional form, as a dynamical system. X of t goes to X of t plus 1, but then you have some residual update. And so this is like a, you have some state, the old state equals the new state, plus some correction. That's what this picture shows, and then you do it again. And so there's been work recently that has said, geez, ResNets really look like they're learning a forward Euler discretization of a dynamical system. And the reason for that is that X of t plus 1, or k plus 1, X of t plus 1, right here, is equal to X of t, this thing, plus an update, plus a R, a residual unit. And if you sneak a delta t plus 1 in here, right, there's no delta t plus 1. You could absorb that into the R, but there's no delta t plus 1. There's actually a weight there, so it's not exactly this, so you could play with that. But let's say that X of t plus 1 is equal to the previous step plus a residual unit. You could sneak a delta t in there, and if you do that, and you've thought, you come from a perspective that thinks about differential equations and dynamical systems, you say, geez, this looks a lot like a discretization of a trapezoid rule or whatever, Euler discretization. And so this looks like a dynamical system. So is this true, or is this just sort of a syntactic, anytime you update something, it's going to look this way? So, so I wouldn't be telling you about this if the answer was yes, they were right. And so here's the spoilers given on the bottom. But, at least as interesting as pointing that out, because you can always point out and say someone didn't do something, quite the way I would. I want to walk you through how we approach this and the MO we took, since I think the MO in terms of evaluating these models is useful much more generally. All right, so what does it even mean to say that ResNet learns a forward Euler representation of a dynamical system, a discretization of a dynamical system? Just having that form, state is equal to previous state plus no correction, I mean, is what Euler sort of looks like, but so do a lot of things. So do discrete things, right? So we want to evaluate this. Ultimately, we're going to evaluate it not in a dynamical system, but we want to evaluate this in a context where a dynamical system is meaningful. So let's look at a time series prediction problem of a dynamical system, and try and evaluate if this is a meaningful statement. And the thing to keep in the back of your mind is that numerical integration theory, we're going to, since you're talking about differential equations and discrete approximations to them, this is what we're going to be using. Numerical integration theory and machine learning really work in opposite ways, right? In numerical integration, you have a ground truth dynamics that's given by your ODE, your PD. You approximate it with a discretization, and then you compute something on that approximation. And the ball game is, can I get a good approximation to this thing with fewer functional evaluations, for example? And so you use Euler or midpoint or RK4 or a range of other implicit and explicit and this and that techniques to say, I want to approximate this ground truth thing with fewer functional evaluations, for example. So that's your model of fast. How many function evaluations do I need? That's like matrix vector multiplies. So then, I want to be fast in terms of approximating this. So as a ground truth, I cut it up, I discretize it, and I want to approximate this continuous thing. When you're learning the dynamics, you're really working in the opposite direction. I just give you a bunch of data points, and I use that to optimize a model. And then I want to know, what is that model? Now, I can apply this if there's a ground truth dynamics. I can apply this if there's not a ground truth dynamics. And so what would it look like to apply this when there is? Do I get something consistent with numerical integration? And then what would it look like if I apply that same methodology when there's not a ground truth dynamics. So that's what we're going to be doing. So revisiting a simple dynamical system, remember the residual makes sense in the context of updates. Future is equal to now plus a delta update. Let's study training such that capital F of X is based on a neural network G. So X of T plus 1, all right, T plus delta T, is equal to F of X of T, which is equal to X of T plus G, your delta. Call that a numerical method. It's a numerical method acting on G. Could be Euler, could be midpoint, could be RK4, could be any of a range of other things. Numerical integrators approximate the integral with a discrete series of applications of, let's call it F is equal to dx dt for time step delta t. So X of T plus delta t is equal to X of T plus the integral from, wherever T to T plus delta t of the function. And then you approximate it and you say that X of T, that this X of T plus delta t is equal to X of T plus some numerical update scheme, which may depend on F or X, could depend on T explicitly, could depend on delta T, So syntactic similarity is really not sufficient to say something is a discrete approximation to a continuous operator. So approximations to dynamical systems, discrete, I should say right here, discrete approximation to continuous dynamical systems really have much richer properties. So if you take a textbook on numerical integration theory or the numerical integration practice might not go into this as explicitly, but certainly numerical integration theory, you'll see, you'll see conditions like this. So for a given integrator, as delta t goes to 0, my error should go to 0, something like time step refinement. Different integrators may go to 0 at different rates, so different rates of convergence. So let's say the log of the error, quantified in some norm or in various ways, is proportional to r, some number by log of delta t. And so there should be better and worse. So there's an asymptotic thing, there's a rate, how quickly you go. The same dx dt, so the same continuous, the same continuous derivative with different integrators should approach the same solution at their respective rates. Right. So these are things we can check, right? These are the things we can check if we start with something continuous and discretize it. These are things we can check if we start with something discrete and try and say it's meaningfully continuous. And so let's call these things convergence tests. So we can check these with a convergence test. And these conditions really are critical for deriving integration schemes, and they're good for tests for numerical software and arrays. So this is not particularly new. This is textbook for certain areas of scientific computing and numerical analysis. So does ResNet satisfy these properties? If yes, then we should be able to, then it will pass those tests. And if so, we should be able to do certain things. We should be able to alter the model. We should be able to take the basic model, given G, X of T plus 1 is equal to X of T plus delta T G. And we should be able to increase or decrease delta T. We should be able to take the frozen G and plug it into other computational graphs. X T plus 1 or K plus 1 is equal to X of T plus delta T. G acting on X of T plus delta T over 2 plus G. So this is starting to look like midpoint. You could do that again. Starts to look like RK4. So if you're familiar with these sort of techniques, you got to get all the coefficients to cancel the right way to get your order of convergence properly, and I'm hiding that. But you should be able to plug this into other computational graphs where you fix the weights on those graphs to instantiate those, those various terms that cancel to various orders. So you should be able to do that, and the predictions should change in a consistent way. If I make, in particular, the model deeper, since that oftentimes corresponds to 1 over time, something should get better, because the time step's getting smaller. So does ResNet satisfy these properties? If yes, then I should be able to do all this. If no, then I should fail those previous tests. And if I try and do this stuff, this shouldn't work. And it should just behave, it might be a better model than this would suggest. It might be a worse model. I haven't said anything about that. It might be better discrete model, but be less flexible. But it shouldn't work, and it should behave differently with respect to delta T than these predictions. So that's the approach we're going to take. So let's take a data set with 1 delta T. We're fixing delta T, and we're generating the dynamics here. We'll apply it to ML data later. We're generating the dynamics here. Train 3 models using a given G, shallow 10H network with 50 hidden units. I don't think there's anything special about that, so this setup. Then we're going to freeze G and perform a convergence test, this thing I talked about on the previous slide. And the hypothesis is that A and B and C, the 3 conditions previously, should hold. And we're going to train 3 different models. We're going to train a Ford-Euler model. This is just the vanilla Ford-Euler. If you're a numerical analyst, you're probably uncomfortable in your seat now because you wouldn't even think of using Euler, but it's a textbook thing. And it's what people say ResNets are. So this really looks like a ResNet. Maybe we'll use midpoint and we'll use RK4. And there's a couple of variants of it. We looked at all of them, at least the 2 main ones. We have ground truth. We're going to apply it to an oscillator, not a linear harmonic. It's a non-linear, but it's one that we have a closed form solution for. And so we'll be able to compare against that ground truth. So its time derivative is equal to alpha, sine of the variable, not the variable. So that's not just a linear. It's 1 step beyond a linear harmonic oscillator. It's not, we have a closed form solution to compare it to. So after we train the models at that delta t, if we evaluate it on that graph, they all do well. All right, so we're adopting this approach. Remember, we have 3 different models that are trained in these 3 different ways, delta t, and we're evaluating them. So we're doing a usual training test split. So the ground truth is blue, the green and the red. The blue and the green and the red, you don't even see them here because they're on top of each other. So they're all the same. They're all very good. This is the time variable, rho against the time variable. This is v, your position and velocity. And similarly here, they're both good. The thing that's not good is numerical Euler. Let's say that we take the dynamical system that we're working with and we try and approximate it with no machine learning, just the Euler technique. It does okay for about a cycle and then it wanders off. It does okay for about a cycle, then it wanders off. So that's not so accurate, but that just says Euler method's not great, which people already knew. Okay, so now let's start to play with this. Let's change the delta t, and if we change the delta t, if we cut delta t in half, now the orange, you see when it was not so good, the orange gets better. It starts to wander off eventually, but the orange gets better. So numerical Euler improves. Good, we cut delta t in half, it improved as expected. Neural RK4, when we learned with the sophisticated integrator, is still on top of the analytical solution. I should have had the colors here. So RK4 is red and Euler is green. So red and blue are still on top of each other. The green gets worse. Green gets worse. So now I cut the time step down a quarter, green will get worse still. So as I'm changing the time step down, I'm getting a worse solution, which smells like it's not going to, I'm not doing what I'm saying I'm doing when I'm approximating a continuous system. One-off plots aren't sufficient. This sort of, is a one-off plot. Let's try and look at this in a more systematic way. So for each of these plots, I can generate a point on this curve. And look at the left. The left, there's a lot of information in this figure. So what I want to do is look at more time steps to the left. 1 over delta t is the depth of the model. So I'm learning what the delta t equals 1. I can vary that. And forward Euler, the base case is black. Midpoint, the rate you'd expect just from them is given black for Euler. Midpoint RK4. And as I change delta t with the same graph, what do I get? If I look at the learned model, and then as I change delta t using the methodology from 2 or 3 slides back, the machine learning model sort of tracks forward Euler, then gets very, very good, orders of magnitude better, then gets worse. So you see a big spike there. For midpoint, it tracks the slope of midpoint until some level, and then it levels off and flattens off. Still going down, but more gradually. And then RK4, it gets much better very quickly and then flattens off. So for large delta t, these models track the integrators, and then at some point they hit sort of a basal level, I'll call it machine learning noise or something, and then flattens off. The point is for midpoint and RK4, this is very smooth here. It's continuous essentially. For Euler, you see a big dip there and then increasing. This is error, down is good. So Euler is a good discrete model. So there's no complaints about that. If you want to do machine learning, training test generalization, the fact that this is so low is good. The fact that if you cut the time step in half or multiply it by 2 or cut it in quarter or multiply it by 4, you get orders of magnitude worse, it really means it's not a good continuous, it's not a good discrete approximation to a continuous model. So you're not really learning a continuous model. You can try different integrators. Remember, we learned one, you plug it into the other. And what you see here is that if you learn on the simpler one, you start with Euler and go to midpoint or RK4, you don't do well. If you learn midpoint and go to Euler, don't do well. If you learn midpoint and RK4, you do as midpoint would suggest. And if you learn RK4 and then use midpoint or Euler, you do as RK4 would suggest. So you're really, if you learn one integrator and then evaluate it with another, you're learning what you'd expect, the more sophisticated one, all right? So, so this really shows, and a range of other evidence, but ResNets are not, discrete approximations, are not, Euler approximations to a continuous dynamical system. You fail these convergence tests. You fail these convergence tests. You can use more sophisticated integrators to pass the convergence tests. So ResNets really are not learning in a meaningful sense. When I say meaningful sense, what you would mean to approximate a continuous dynamical system. So they're not really learning a continuous dynamical system. They're good discrete models. There's no argument about that. And if all you're interested in is training and testing and so on, they're good discrete models. They're not really learning a continuous dynamical system. In a lot of cases, that's fine. You don't need to learn it. Just don't worry about this. But if you really want to learn a continuous dynamical system, that should be a real issue. If you want the stability or the robustness or a range of other properties, that could be a real concern. So these slides are up on my web page, and this, look at any given point, look at the delta t equals 1, delta t is larger. So these just walk through in a little bit more detail what I was just describing. So if you want to look in a little bit more detail. So the implications here are that I think the prevailing training MO, the prevailing training methodology that ML people use, does not yield models that can be used as continuous dynamical systems. It can be interpreted with continuous theory. So you'll see a lot of work on neural ODEs, and what they do is they put a T somewhere and they sort of learn something that superficially looks like a differential equation, but which doesn't pass these convergence tests. So you can call it a continuous differential equation, but it's failed all the convergence tests. We have something that is meaningfully continuous in depth in that sense that does pass these convergence tests. Having a peak that is fragile to the number of time steps means you can't do interpolation, which is what you want to do. If you're saying this is a continuous model, delta t, you cut it in half, there's something continuous. I mean, people don't do this to say, I'm learning a continuous dynamical system, and then they're going to do functional analysis and put wildly pathological functions there. They want to work with smooth functions that you find in engineering. And so the RK fork scheme allows us to do this. And you might be interested in dynamical systems and engineering and physics ML. You might just be interested in ML that's not that. But in either case, the analysis here can be seen as a diagnostic tool to assess if the model's overfit. So we have a range of other ways using Hessian loss landscapes to sort of justify the claim that the dynamical systems really are much choppier, and the continuous ones, the ResNet-based dynamical systems, are choppier. The ones that are meaningfully continuous in depth are much smoother. So in the last few minutes, let me just wrap up and say, so we use this to develop what we call continuous net, a meaningfully continuous in depth neural network. It's a deep model that is a dynamical system. It is a dynamical system in the sense that it's a discrete thing, but it passes the convergence tests that say it's a discrete approximation to a continuous thing in that meaningful way. Basis functions in depth for parameters, higher order Runge-Kutta scheme for the computational graphs, the right time step refinement and grid refinement. And it's really sort of a plug-in. I mean, so you can use, you can recover ResNets for certain choices of basis functions and graphs, but it's much more general. It's a plug-in, but it's meaningfully continuous in time in that sense. The basic equations for continuous net have these time-varying parameters. Blocks of residual units can just be replaced by numerical integrators, and you assemble the ODE blocks in, you could vary this, but in the simplest case, just into the same architecture that you have for ResNets. Importantly, the governing equations has time-varying parameters. The parameter now is a function of time. We don't have time explicitly here. And so this gives continuity over depth. You could choose these to be step functions, and in the current paper we have that, but we have follow-up work that we're working on where these are smoother functions. If this is your basic ResNet block that you chain together, you could use a midpoint block and chain this together. You could use a classic RK4, you can use an RK4 3/8, and you just chain it together. And this is a black box module. And you got to choose these parameters. These are not parameters to learn. These are forced on you by the dynamical systems, but you can learn the other parameters if you want. And again, I have arrows here to walk through. There's a range of things that we have hello world results on. That, parameters are more smooth as a function of time, and a range of other things that that you might expect and that I think are the case. But this opens up a lot of questions for doing that sort of in a more principled way. Continuous nets computations are assigning weights by evaluating a continuous function theta. What does it mean to evaluate halfway between two time steps? So essentially what we do is we have functions theta as a function of t, and we do the usual thing you do. You represent those functions in some basis, so you implicitly define the function by the basis expansion. And so really learning the parameters. And if you choose a special case of a given depth, the number of functions equals that depth. They're all step functions with unit value at one layer. You can recover the ResNets, the ResNet models. But this is just a much more general way to, and then you wouldn't have continuity between layers because the basis functions you're learning are step functions at each layer. So, but here these can be anything smooth in time. If there's step functions between each layer, you don't have a natural way to do refinement. If you have a function that's smooth and has some derivatives that are smooth as a function of time, then you could say chop this up into 10 layers or chop this up into 20 layers. And the layers I learned are, one is a refinement of the other. But ResNet is exactly Ford Euler, as I said, if you use piecewise constant basis functions, but that's not the case you should be thinking about. So we want to apply this to image classification, and let me just wrap up with that. So I think there's a range of things that we've opened up here for doing in a reasonably principled way, learning dynamical systems using continuous sort of scientific computing ideas, where you're really meaningfully continuous in time, where you can control the error relative to a continuous model. And that's good if you want to learn continuous dynamical systems for dynamical systems / physics / engineering plus ML. You might say, I don't care about that. I want to apply this idea back to image classification or to natural language or whatever. So you can apply the same test we did in those areas. You don't need a dynamical system. You've hypothesized this. And so you could hypothesize this in those image classification and natural language examples, in which case it's essentially a modeling assumption, which is fine. And so you might do this and hope that if this works, you can expect training with midpoint or RK4, one of these other better numerical methods, to enable us to transfer between depths or graph modules in sort of a meaningful way. I'll wrap up with, well, one or two after this, but with this figure, this is the usual plot you'd see in machine learning, something, depth, test error. So this is the plot I showed you before, except I showed you before the plot in a way that on log scales and in a way that a scientific computing person that was doing convergence tests would view it. This is the way a machine learning person would view it. And so what we see here is that we can perform the same tests on CFAR10, and we've done a range of other things. Train continuous net 32, 32, 32 with RK4 on Euler. And what you see is that with Euler, this thing goes down at 32, hits a minimum, good, but then goes back up and gets sort of large and gets choppy. RK4, it just goes down smoothly and stays down. So the fact that you have a dip here, right there, and then you go back up is the same dip we saw before. So you'll see this here. You'll see it more prominently on the next slide. And you can do the same thing where you'll learn RK4 and plug it into Euler, vice versa. And what you see here is, red and purple slightly more slowly just go down and are pretty smooth, whereas green is just very, very choppy. So green is when you learn it with Euler, the traditional method. Deeper is to the right here, shallower is to the left. And again, arrows if you want to walk through the plots online. So you see the same sort of thing with CFAR10. You see it a little bit more prominently with ImageNet. I mean, the point here is I think you have a dip and then it increases with depth, the blue, which is Euler, which is what you'd learn just using these traditional ML techniques. But you get what I think is probably sort of oscillations, higher order harmonics, or maybe some sort of aliasing here. So I think there's a lot of room here for someone with an engineering or signal processing background to extend and do nice things here, because these it look like, I think, are sort of higher order harmonics. And so you may say, why do we care about this? Orange is behaves smoothly, but blue is marginally better. So we probably could have tested this to death and made orange marginally better if we wanted to declare success that way. But we just wanted to highlight, if you use existing ML techniques, you really care about this being marginally better here. You don't care about the smoothness properties, the depth properties, all these other properties that you might care about in scientific computing here. So I have a couple slides here. So the basic idea is there's many computer programs for a given problem, and we're going to choose one that's continuous. So this is a modeling assumption. And that's a good model or a bad model, but it's a modeling assumption. And you can apply that even when there's not an underlying dynamical system. That's the bottom line. So I have a bunch of tables with numbers that shows that we're good. And I think there's a range of things in terms of refinement during training, but also during inference that I'm just going to not go through this in the interest of time here, but that I think are natural sort of follow-ups. So let me wrap up, and I think I have Okay, so ResNet, I think, really sort of overfits a continuous dynamical system. And there's a lot of attention on neural ODEs and so on, but I think the evaluation mechanism makes it almost impossible for them to be continuous things if you use training and testing errors. Physical time series models really are improved by embedding inside a higher order integrator. This isn't going to higher order just gratuitously because we like higher order integrators. This was because we needed to do that if we wanted to be meaningfully continuous in depth. And we can find deep dynamical systems that are as expensive as ResNet using basis function weights. So let me wrap up there. I think there's a range of things. Vanilla training is slightly more expensive. You're probably more robust to hyperparameters. There's a range of other follow-up sort of questions that you could look at, and I'm glad to answer any questions. But just let me wrap up so that if people need to go on the hour or something, then they can. So thanks for your attention.
All right, thank you, Michael. Really great presentation. I have a couple questions, I think, in the chat box. I can read them for you if you want.
Sure.
So first, in the physics-informed learning, what kinds of physics, other than stability information, can the encoder-decoder architecture incorporate? Can we incorporate partly known information about the system, few constants, structure of the ODE?
Yeah, I mean, we haven't looked at that. I mean, some people have. So you can, I mean, in a sense, I mean, there's two ways, I guess, that if you're talking about in terms of the architecture or in terms of the constraints, but I mean, in principle, you could encode them either way, I guess. I think right now you're sort of in this Wild West expansion phase where people are playing with lots of different ways to encode things to figure out what are the best. And I think part of the answer to that question, do you put in the architecture, do you put it later, depends on, I mean, if you're stress testing things and you're taking months of GPU time versus you're doing something in a couple minutes, because a lot of the decisions, are constrained by hardware software systems. And that's changing just because of changes in Moore's law and Dennard scaling, if you're familiar with that. So I don't know that the answer now will be the same as the answer as it would have been in 5 years or 5 years ago. But there's all sorts of different things you could impose there as constraints. People cook in symmetries, people cook in temporal invariances, people try and do a range of different things. And the best way to do that, I think, is still in flux.
All right. So we have Patrick who wants to ask a question. I'll ask you to unmute.
Okay. Hi, can you hear me?
Yep.
Hi. Yeah. So you've been talking about continuous net as somehow distinct from neural ODEs, but in most of the neural ODE literature, people would be using something like an adaptive step size solver. And at the very least, they'd probably never use anything below an RK4. I don't think I've seen below RK4 used. So I was just sort of asking you to comment on what you see as being the distinction between continuous net and just the usual neural ODE setup.
Yeah, so I guess the question there is, what does it mean to be a neural ODE? I mean, I feel like this is a term that, and this is a lot of times when you get a new idea in an area, right? There's a paper that gives a name, and when the name taps into something, the term means more than the original thing, right? Anything that looks a little bit continuous, and anything that sort of might have an integrator or an adjoint, it can then be called a neural ODE. So if you want to view it at that level of granularity, you can call this that. I think that something that people, and actually we put this up 6 months ago, whenever, and this is a paper that has 4 ideas, which is always a bad thing if you have more than one idea in a paper, because people get confused, right? It has the continuous thing. It has the evaluation on the methodology. It has the evaluation on the CV data. There's papers in the last 6 months that I think not as thoroughly as we did here, but address each of those issues. And subsequent to this, our result coming out. So I think people are realizing that call it neural ODEs are not meaningfully continuous, that they don't satisfy some of these properties. And so the area may evolve, and those things get solved, and all of these go under a neural ODE umbrella. That's fine if that's the way it evolves. I think people sort of paint with a broad brush, and when you really ask them what is a neural ODE, it either means what was in the first paper, but that was a differential equation that they were trying to integrate backwards in time, and they evaluated on something where you really didn't need to do more than 2 steps, which was the genesis of A-node and A-node V2 that I mentioned at the beginning. So if you want to call all the subsequent improvements there neural ODEs, that's fine. But if you want to say, what people are doing and what people are claiming, there's a bit of a disconnect. And so we're just saying this is something that passes convergence tests and is distinct from that in that it has a different metric, quality metric and construction metric.
Okay, thank you. And just for what it's worth, to sort of offer a contrary opinion, I feel like a lot of the literature on neural ODEs does try to aim for something continuous, and this is done through things like adaptive solvers, because the issues you're describing, they've been highlighted before. Sorry, I'm not trying to start something there.
I think they try to. I don't disagree. Yeah.
Anyway,
I think they're motivated by it. I guess I haven't seen them close the loop in this way, but I think they're certainly motivated by that, and in that sense try to. Yeah.
Anyway, I should pass the baton on to someone else to ask a question.
All right. So one other question. For the continuous time machine learning, in classic scientific computing, implicit integrators are needed for numerical stability of stiff equations. Is there a similar challenge to stiff equations in your machine learning approach, and are there analogs to implicit steppers?
Yeah, there can be, and there probably will be. We're looking at one version of that. I think it may take one of 2 forms. I mean, you certainly, if you have a particular stiff dynamical system that you're looking at, then you could use a different integrator there. And so we're looking at that. I think you could also say, what's the analog of 2 very different timescales for problems beyond just one where you're learning a dynamical system where you have 2 very different timescales, and then try and, in the same way as we did here, learn a dynamical system, but apply the same MO back to CV or NLP. And there's a range of things sort of in attention models in NLP that, seem like they might have a similar sort of structure, in which case it would be interesting to see if the ML techniques to using different integrators to learn a stiff differential equation could be applied there fruitfully also. So I'm sure other people are looking at that. We're looking at that, yeah.
Right. I don't see any other questions. I have a question actually. So it's very interesting how you're using sort of a recurrent neural network to approximate an integrator. And I think with like physics-informed machine learning, the issue has always been that these constraints are satisfied only, so they're soft constraints, not hard constraints. And that's why they suffer robustness and stability issues. And so, but at the same time, the motivation is that we want to combine data with numerical integrators. So do you think in the future that the neural networks in general, or machine learning techniques, will reach a certain maturity that they become robust enough that they replace traditional integrators completely, or that's not possible? What do you think will happen in the future?
I mean, there's times you want to just do numerical integration, in which case you probably should do it, right? I mean, I don't know if it's, you still have to learn something, right? And so what do you learn from? I mean, in some cases, we would learn from simulations that were used with traditional numerical integrators, right? So why, I don't know if it's a replacement as much as, I mean, a different complementary set of methods that in some cases, I think it expands, this data-driven stuff expands the scope a lot for what you could do, but I'm sure there'll be a core set of things that you wouldn't want to do this for. So I don't know that it will be sort of ultimately a replacement as expand the scope of what you could do with those older techniques.
Okay, thank you. And let me see if there's someone. Someone is telling me there are more questions on the chat. Okay, so there was a question I skipped, which is for problems which require more than just prediction, say for example, controlling a system, how do we quantify the errors in using continuous nets so that we can learn controllers robust enough to account for uncertainties?
Yeah, I mean, that's a lot of keywords in that question. I guess I think there's a bifurcation in what do you know about the domain? If the question is, I want to learn something to control a very physical or engineering thing, you probably have a lot of domain knowledge, and probably the way you'd use this is to not put that in the learned ML model necessarily, except maybe weakly, but control it sort of outside the process. So you could have a control system that controls, the performance of the model. If you're applying it to CV or NLP, other things like that, I mean, you could do that, and that's sort of what people currently do. You may be able to put it in, but again, I guess I don't know what the exact objective is, right? You could add a hard constraint on stability. You can add a soft constraint on stability, but a soft constraint on stability might be means that you're unstable. The reason I think that prediction, classification, and regression, and these things get a lot of attention is just very well-defined objectives. It's not I'll say a soft thing like even stability, right? Because there's various notions of stability, and one might be theoretically easier, one might be practically more important. Then you're getting into a debate, right? I mean, classification is just a number. I just want that number to be higher. So I don't know of an analog just to sort of plug, what that objective would be on stability, just to plug it in sort of an automated way. There may be one. Yeah, I don't know.
All right, one last question. So have you tried symplectic integrators and baking in action conservation to see if predictions improve? Hamiltonians play central role in sensible dynamics. How does high dimensional nature of data play a role?
Yeah, so we haven't. I'm sure other people haven't. It's on our list of things to do. I mean, we're sort of currently looking at how the ideas we had to evaluate whether something's meaningfully continuous applies to sort of a range of other dynamical systems, and then we'll iterate on that. And that's one of the things we've sort of thought about. So I know that others have. I don't know the exact results they have, and that's in the pipeline for us. But we don't have any sort of results currently on symplectic integrators. I mean, there's a range of things that you get in terms of, I mean, to conserve global invariance that you could fold into the integrator. But yeah, that's in the pipeline, but we don't have any results on that yet.
All right, I think there are no more questions. Thank you very much. It was great. It was great talk. It was great having you on the seminar, and I hope we see you again soon.
Oh, thanks for having me. This was nice.
That was great. Yeah, thank you.
Hey, Joe,
Yes.
you're still recording.
All right.